After considering the dislocation, which is a one-dimensional defect, let us now proceed to two-dimensional defects, and we have already described the inevitable one, which is the surface in any practical crystal. We will also consider the grain boundary, the twin boundary and the stacking fault apart from the antiphase boundary when we discuss two-dimensional defects. For those who are interested in taking a little advanced reading, they can consider the book by Kelly and Groves on crystallography and crystal defects. Let us start with a broad overview of the possible two-dimensional defects and perhaps more than one way of classifying the same. So, if you are looking at two-dimensional defects, you can have a crystal boundary, and this crystal boundary can be a crystal air or a crystal vacuum interface, which we call a surface, or it can be a crystal kind of an interface. Apart from this, there are stacking faults, which are two-dimensional defects, and there are twin boundaries. And a special kind of stacking fault is also called an antiphase boundary, and we will consider that at a later point during these lectures. When you are talking about a crystal interface, you can either talk about a crystal homophase interface, that means the material on two sides of the crystal has identical structure, in which case you call it a grain boundary, and or it can be a between two phases, in which case it will be called an interface boundary. We will also consider special cases of this grain boundary, which we will call the low angle grain boundary and the high angle grain boundary. So, to summarize this slide, we have various kinds of two-dimensional defects like the crystal boundary, the stacking faults which lie within a crystal, and a twin boundary, which is a special kind of an interface. And amongst the crystal boundaries, you can have either a surface or an internal interface, and if you are talking about an internal interface, then you can have between two different kind of phases or between phases of the same kind. Let us look at the same classification in a different way, that you have two-dimensional defects and they can be the external or the internal. We are talking about external, as I said, typically we consider a surface as an interface between the crystal and the vacuum or crystal and air, and internal interface could be between the same kind of phase, which we call a homophase boundary, or it can be a heterophase boundary, in which the phases on the either side of the boundary are of different type. Homophase boundaries can be grain boundaries, twin boundaries and stacking faults, and there are special things which characterize these kind of boundaries, like for instance, a grain boundary is characterized by rotation, a twin boundary is characterized by its association with mirror, inversion or rotational symmetry, and a stacking fault is associated with a translation vector. There are special cases of stacking faults which are the antiphase boundaries. Grain boundaries themselves, as I pointed out, can be low angle or high angle, and the reason for such a classification also will become very clear once we discuss the structure of these low angle grain boundaries. Now, the alternate way of looking at some of these or characterizing some of these homophase boundaries, which we shall contrast with heterophase boundaries, is the way we look at them from different perspectives. We can look at a homophase boundary based on the angle of rotation, in which case you can have a low angle or a high angle, and in this case we are talking about the value of the angle of rotation, in which case they will have a low angle or a high angle homophase boundary. Of course, you could also have, under special circumstances, similar kind of definition going into the defining a heterophase boundary. A homophase boundary based on the kind of axis we are talking about can be a twist boundary, the tilt boundary, or a mixed kind of boundary. The mixed boundary will have twist and tilt components both. You can classify homophase boundaries based on the models which are used to describe them. For instance, you can have CSL models describing, which is known as the coincidence site lattice models describing homophase boundaries, and in this context we can call homophase boundaries a special or random. So, if you have a low angle low coincidence site lattice number, which is typically given as symbol sigma, then you call them a special boundary, or otherwise you call them a random boundary. You can also classify them, these homophase boundaries, based on the geometry of the bounding plane, like you could have curved boundaries, you could have faceted boundaries, and of course you could have a mixed boundary wherein certain sections are curved and certain sections are faceted. So, to review this slide, when I am looking at homophase boundaries, I can characterize the homophase boundary based on various parameters. These parameters can be the angle of rotation, or more precisely the value of the angle of rotation. It can be based on the axis which defines the rotation, or it can be based on the kind of models which are used to describe these boundaries, and these models also imply that, for instance, these special boundaries typically have a low surface energy or interface energy value. And based on the geometry of the bounding plane, like for instance you could and these geometries are also associated with the way these boundaries behave under, for instance, if you are trying to coarsen the grain, or you are trying to do one of these processes under high temperature, it will depend, for instance, if the boundary is curved, faceted or mixed kind. So, we will consider some of these for instance, low angle and high angle boundaries and some other aspects in detail, though some of the other aspects we will leave for future courses or higher level courses. When you are talking about heterophase boundaries, you could have three kind of terminologies coming in: a coherent kind of heterophase interface, an incoherent kind of an heterophase interface, or there can be something in between, which is a semi-coherent heterophase interface. So, we will take up examples of these and we will try to understand the structure and in some cases also the stress state of some of these boundaries. So, going back to these slides, we want to classify two-dimensional defects, and in doing so we have come across certain kind of defects whose names perhaps many of you might be encountering for the first time, like the crystal, the grain boundary here, right here, the grain boundary or the interface boundary, or the term like stacking fault, antiphase boundary and twin boundary. And we have alternate ways of doing the same classification and alternate picture, which sometimes is more useful in getting a complete picture or multiple perspectives of the same problem. And also when you are talking about homophase or heterophase boundaries, we come across multiple parameters which go on to define these boundaries, and some of these will be dealt in detail during this set of lectures. Heterophase boundaries, which I think is very important technologically also, is very important understanding the behavior of these, some of these devices and materials which are built out of these kind of interfaces, can be classified as coherent, semi-coherent or incoherent. So, let us start with the most obvious of these interfaces, the surface, and as I pointed out that a surface is an interface between the termination of the bulk with the air or the vacuum. Even though we call some of these surfaces two-dimensional defects, we have to remember that, as before, as pointed out before, that this is two-dimensional only in the mathematical sense, and typically the region of distortion is a few atomic diameters in thickness. In fact, the real surface is always a few layers deep, it is never just a few one atomic layer, because the disturbance which is felt in the topmost layer is always fall out to the next layer. And later on we will see that we will come across phenomena like reconstruction, etc., wherein the topmost layer gets reconstructed in a certain way and the layer just below the top layer can also get reconstructed, but in a different way. So, it is, and even in all those cases we always call these a surface, even though it is never two-dimensional, it extends a few atomic diameters into the bulk. So, how do I create a surface of a crystal? Obviously, I need to cut an infinite crystal, and of course, this is an hypothetical experiment, and I would cut this crystal and I will get two surfaces, right. And this cutting process obviously is going to be cutting the bonds, and that means that it is going to cost me energy to actually create this cut. So, what are the parameters which would characterize such a cut? Obviously, it is going to be the angle of cut, and now I am talking about the angle with respect to the crystallographic axis, and which I can characterize by Miller indices. And the second thing is the position of the cut within the unit cell. So, this is another thing which I need to keep into mind. So, whenever I am making a cut of a crystal, to create a surface, I need to characterize the cut by the angle of the cut with respect to the crystallographic axis and the position of the cut as well. For instance, now suppose I have a crystal on the left hand side, which is shown by the unit cell of the crystal, and I make a cut as shown here. I can change the angle of the cut, and of course, along with this will be accompanied by change in the position of the cut as well with respect to the unit cell. So, if I change the angle of the cut, now I can cut the crystal in a different way. As you can see, the area of this plane is changing, and obviously the kind of bonds which are broken also will change with this. We will soon make some calculations of the energy which it costs to make such cuts, but it is essential to remember that the angle of cut has been changed. Alternately, I can move this plane within the unit cell and change just the position of the cut. So, in this case, the cut, for instance, is a 100 kind of a plane, but the 100 plane has been positioned differently. The cut which is shown here on the top, this one is, so this is my 100 kind of a cut, but now the same 100 has been positioned differently. Now, sorry, I have to draw the plane here. So, this is a 100 cut, and this would be typically a 111 kind of a cut, but I can change the position of this 111 plane and take an alternate 111 cut also within the crystal. The change in such a position obviously is going to alter the kind of surface I am going to expose. Of course, this may not be true for all kind of crystals, but this and all kind of planes, but suppose I am visualizing, for instance, a sodium chloride crystal. If I now change my the position within the crystal. So, I may have a crystal with a surface which consists only of sodium atoms, or I could have a crystal which has only potassium chlorine atoms on the surface. So, that would just be merely by changing the position of the cut within the unit cell. So, suppose I make a cut like this in this position, I could land up with one kind of a surface, and if I change the position I could land up with another kind of a surface, and the two sides of the surface could also be different. Suppose I make a cut like this, then the crystal on the top side could be different from the crystal on the bottom side. So, this is something which we have to remember. So, we will just write this down. So, this is something we have to remember, and therefore, even though I may be given a single plane of cut with, for instance, a 1 kind of a Miller index, I have to remember that if I move the plane within the unit cell, then I may actually be creating very many different kind of surfaces, depending of course on the complexity of the crystal structure I am considering. So, the essential two parameters remain, the angle of the cut and the position of the cut, and of course, once having made a cut, I have to differentiate the two kind of crystals, the two surfaces which it makes, and they may not be equivalent, because the kind of bonds they have below the surface can be different on one side compared to the other side. So, this is something we have to keep in mind. Now, the question we are asking is that after having made the cut and having created two surfaces, and we already mentioned that these two surfaces could be actually be different, then what can happen to the surface? Will the surface remain unaltered, or will it change in certain way? So, of course, the simplest possibility is that it remains essentially unaltered. So, this is my simplest available alternative. But there are interesting possibilities which can happen to the crystal, like for instance, the surface can actually reconstruct. That means the surface crystal structure can become different from the bulk crystal structure, and therefore, the surface is no longer merely a termination of the bulk. Okay. So, this is something which is very important, and we will take up maybe some examples during the later part of these lectures. So, what I am trying to tell in this case is that when I am making a cut, I create a surface which is nothing but a termination of the bulk, but this surface need not remain merely a termination of the bulk and can alter its structure with respect to the bulk, and this alteration obviously takes place so that the energy of the surface can be reduced, because now the cutting involves increasing the energy of the system, because now you have broken the bonds, and this reconstruction can actually lead to the reduction in surface energy. In extreme circumstances, we can also visualize that the surface may actually become less ordered with respect to the bulk, but this is an extreme possibility and we will not consider this further. Now, what is the simplest way I can calculate the energy of a surface? So, the simplest assumption I can make is that after making the cut, the surface remains unaltered and it is exactly the same as the bulk, it is a termination of the bulk. So, in this case I can go ahead and make a calculation of the energy based on the number of bonds broken. So, I can see that it costs energy to put a surface, the system will want to minimize the surface area, and this will result in surface tension. So, before I go into surface tension, let us try to calculate the energy and what are the terms which go into the calculation of the energy. So, the surface energy, which is joules per meter square, because now it is a 2 dimensional, so therefore I have meter square in the denominator, is usually designated by the value gamma, and initially we are considering just the mere surface, what you might call the energy of the surface. Additionally, we can also define terms like surface free energy, like the surface Gibbs free energy, but we are not doing so in this case, and that means we are ignoring entropic terms in this energy. Now, what is the value of the surface energy? Is first thing I need to know is there are number of atoms on the surface. Then I need to know that number of bonds broken when I actually make the cut. Then I need to know the bond energy per bond, right? And of course, I divide this whole function by 2, because now there are two surfaces being created, half the energy would reside with one surface and the other half of the energy because of the breaking of the bonds will reside with the other surface. So, if you calculate the units of this diagram or the units of this function, you will see that it is number of atoms per unit area, which is Na, and if you multiply that by number of bonds broken per unit area, so this is the second term and this is bond energy per bond. So, you will get that multiplication of the 3 units will give you energy per unit area. So, you will have this energy per per unit area, while this bond and this bond term will cancel with this bond term here, and this, for instance, this number of atoms term will cancel with. So, you will end up with this is just a number of atoms per unit area. So, you get this area term from there. So, what does this mean to have a surface energy when I make this cut? It means that the surface will always want to be reducing its area and will try to pull upon itself. This is an important thing. That means that my crystal system does not want to have a large surface area, it will try to minimize the surface area. Atoms on the surface will want to come towards each other, and this implies that the surface is in a state of tension, which is known as the surface tension. As you will see later, the term surface tension is better used in the context of liquids, and the term surface stresses is better used in the context of solids, and we will state the reasons why. But nevertheless, the origin of the surface tension is coming from the energy which is expended when I am trying to put a surface. Now, we will make a calculation showing that how this formula can be used in the calculation of surface energy, but you have to remember this is what is called a broken bond model. In other words, that I do not incorporate any other effects like surface relaxation after the cut is made, or any kind of reconstruction effects, and therefore, this is the simplest kind of formula I can deal with. Now, another important effect of the surface energy is that given that the surface is a state of high energy, and also the fact that the surface has higher freedom compared to the bulk, the atoms in the surface can vibrate or have a higher degree of freedom as compared to the atoms in the bulk, that the melting point of the surface will be lower than the melting point of the bulk. That means the surface would melt at lower temperatures as compared to the bulk. Additionally, the surface is a region where the diffusivity of species will also be much higher as compared to the bulk. So, wherever I have a diffusivity issue and there are a lot of surfaces in the system, then atomic species will rather be transported to the surface, even though the cross section available through the surface may be small, but it will definitely be transported to the surface as compared to the bulk. A good example would be, suppose I had a material, a polycrystalline material here, and you had a vertical boundary, a grain boundary. So, what will happen is, suppose I heat such a material, then due to surface tension balance, you will see that a small groove would be formed, and typically this groove will tend to deepen in this material, and this is purely in the effect of temperature. So, I have a boundary which is deepening. Now, in this case, for such a deepening to take place, mass transport has to occur from regions here where there was material to the surface, and this can take place either to the bulk or it can take place to the surface. But essentially it is observed in such problems, it is the surface diffusion which is playing a dominant role, because there is the diffusivity of the surface, because of the available freedom of the atoms to be present there is much higher than the bulk diffusion. So, we have a formula for the energy, and this formula has 3 terms to it: the number of atoms per unit area, the number of bonds broken per unit area, and the bond energy per bond. If you look at the surface free energies of some crystals, this is listed here, you would notice that some of the ionic crystals, sodium chloride etc., have a lower surface energy as compared to copper, and of course, in the case of sodium chloride we have to worry about the kind of surface we are talking about, and we will come to the details of the kind of surface very soon, because typically surface energy is not isotropic, and that is the reason, suppose you have an equilibrated crystal, you will notice that the surface is never, if you have, of course, you have to equilibrate the crystal for a long time, you will be notice that it is actually a polyhedral surface that a crystal would like to put out. Now, but you can see that the order of magnitude of the surface energy is about the order of about a joule per meter square of the surface. Now, I had mentioned that a surface of a solid is considerably different from the surface of a liquid, and they have to be differentiated, and it is not only that, the number of parameters which go into this definition itself is very different. Suppose I had a liquid surface, the essential difference comes, suppose I stretch this liquid surface. So, what would happen is that the surface area is increasing by stretching. Suppose I could take a soap film, for instance, as an example, I could take a soap film between 2 sliders. So, I am looking at the soap film from the side, and if you look from the top, suppose I have a slider like this and I have a soap film. This is my side view here, this one, and I am stretching these. So, I am stretching the soap film across these sliders. So, what would happen is that as this film is stretched, the surface area is increasing, right, and but then atoms in the subsurface can actually come and sit on the surface. So, I have my surface, atoms below can come and sit on the surface, and to accommodate this stretch, in other words, my surface structure remains unaltered with respect to the stretching. So, as I keep on stretching, more and more atoms come to the surface, and the surface structure remains unaltered as I am stretching this material or this soap film. But I am suppose stretching a solid. Obviously, this is not true, at least at normal temperatures, at wherever the diffusion rate is very small, this is not true. Now, this makes a liquid surface considerably different from a solid surface, and let us look at some of the terms which are used in defining solid and liquid surfaces. Obviously, both of them are associated with surface energy, which is coming from unsatisfied coordination. In the case of a liquid surface, a term like surface tension will be used, while in the case of a solid, the appropriate term is actually surface stresses, which is actually a tensor. And the difference between the two will become obvious when you go to the next slide. And in the case of, if I want to characterize a liquid surface, I need to characterize just by one number, which is the surface density of atoms. And more importantly, liquid surfaces cannot support shear stresses. They can support normal stresses, but not shear stresses. A solid surface, apart from being characterized by actually by surface stress instead of a surface tension, of course, we could always calculate a surface tension based on the surface stress, but we will see that this is not sufficient, and actually the surface stress is a better term to define a solid surface. But additionally, a surface is also associated with something known as a surface torque. The origin of the surface torque we will consider very soon, but more importantly, let us first consider the term surface stress and its difference between the liquid and the solid. And suppose I want to characterize a solid surface, we have to remember that if I am talking about a crystalline surface, then all the lattice constants will be required to characterize my crystalline surface. Amorphous surfaces can be characterized by the density and a sort of a short range order parameter. So, what is the surface tension and why is it different from the surface stress? Okay. Suppose I have a surface is obviously a two-dimensional defect, and therefore, I will have four components to my stresses. I can define a surface tension as the average of these stresses in two orthogonal directions. So, that is my surface tension. But now, because if I am talking about a solid, I need all the four, of course, it could be a symmetric tensor, I will have three independent components to this, and you will also have shear components, which of course the liquid surface cannot support. Therefore, I have to remember that surface stresses is a better term to describe solid surfaces, and I can calculate, of course, the average of the two orthogonal stresses, which is nothing but which is analogous to definition of hydrostatic pressure in 3 dimensions. So, this kind of an average is nothing but analogous to a 2-dimensional version of the 3-dimensional hydrostatic stress. So, when I am working with liquid surfaces, I can use the term surface tension, but when I am working with solid surface, I need to use the surface stress as the describing quantity. The surface energy can alternately be defined as the reversible work done to create a unit surface. So, this is an alternate way which is based on the energy which is input actually to create a surface, and this kind of a definition works beautifully when you are, of course, the kind of experiment I am talking about, wherein you have a slider in which you are pulling a soap bubble or a soap film, sorry. So, it is now clear that when I am talking about a solid surface which can now support shear stresses, I need to be a little careful in the way I characterize a solid surface. An important point to note is that I am pulling the surface, the solid surface will actually alter its structure, the bonds on the surface will be longer, and it will no longer maintain its original structure before the stretching process began, which is what we can assume in the case of liquid surfaces. And additionally, as I said, there is an additional term which you need to worry about, surface torque, the origin of which we will take up soon. So, to summarize, the liquid surfaces are characterized by a single parameter, the density, which is the atoms per unit area. There is short range order in liquids, but this order is varying in time, and therefore, I cannot ascribe any further structure to this liquid surface. The crystalline solids have a definite structure in 3D, and additional parameters are required to characterize the surface of these crystalline solids, and more importantly, the order on the surface of the crystal can be different from the order in the bulk. So, that is why a surface can have an independent entity or existence or description as compared to the bulk of the crystal. So, this is very important to note. An amorphous solid have only short range order, but no long range order, and so this is why an amorphous surface would have to be characterized very different from a crystalline kind of a surface. So, what is the structure of a surface that we are talking about? Typically, it is obvious that if I have a crystal which I have created and I anneal this crystal for long times, this crystal would like to put up low energy surfaces, right, so that the system cost to the energy is small. What kind of a construction we will briefly allude, so that we know how to arrive at this kind of an equilibrium surface construction, though we will not go into detail, but we will at least tell the methodology which is involved in understanding how this surface, what kind of a surfaces the crystal will put out. But nevertheless, it is clear that there are these low energy planes, and these low energy planes typically are the crystallographic low index planes, right. So, the crystal suppose puts out these low energy planes, these can be atomically smooth below the roughening temperature. So, roughening temperature is the temperature above which actually the surface becomes very rough and it is no longer actually nice to talk about these flat atomic planes. Okay. But essentially, suppose I am talking about a crystal at low temperatures, that means that I can talk about these low crystallographic index planes which are low energy planes and they are atomically smooth. Now, if I go off this low angle, that means I no longer work with low index planes, but I am off the angle in which this inclination of these low index planes, then the structure of these kind of planes can be described by terraces and ledges, and we will see picture of this in the very next slide. These ledges which I am talking about are structural ledges. So, this is very important because these ledges are not random ledges, they are structural ledges and they accommodate the inclination. So, like we talked about in dislocations accommodating inclination between two grains, and which is we will consider a little more detail in this chapter, where we are talking about low angle grain boundaries which go on to accommodate the inclination between two grains. Similarly, an inclination of the surface is accommodated by these structural ledges which form on the surface, and this is how they look. Suppose I have a low index plane to start with. For instance, let me draw a low index plane. So, suppose I have a low index plane like this now in a crystal, then I make a cut which is at an inclination to this low index plane, for instance here as shown here at an angle theta for instance. Then this low index plane is not a plane which is continuous, but it is accommodated by the presence of terraces like these blue marked regions which are terraces and ledges, and as I pointed out, these ledges are structural ledges, and in principle these ledges would repel each other and therefore they will tend to be as equispaced as possible. So, now when I am going off this low index plane into high energy configuration, the surface breaks up into two components. One is the surface, a terrace and a ledge, such that both of these correspond to low energy, and therefore, the system energy is minimized by putting out not some arbitrary inclined surface, but a surface which has low energy inclination, which are bounded by planes which have low energy. So, this is a very important point, and these ledges interestingly can be classified as a defect in a defect, because surface itself is a defect which is now a termination of the bulk in some sense, and these ledges are a defect in the surface, and therefore, they can be thought of as a defect in a defect. Now, suppose, and this defect arose because now I had inclined my surface in one direction with respect to the original free surface. Now, I can cause an inclination in the other direction as well. That means, I have a further inclination not described by one angle theta, but the other direction as well, and in that case you would notice that the surface is accommodated not only by the presence of these ledges and terraces, but also by kinks in the ledge. And interestingly, you can see in this figure which is the bottom, I am showing here figure at the bottom, that these are the kinks. So, originally you had just a terrace which is the free surface here, which you can call a terrace. It broke down into ledges here and the terraces, and these ledges again had an orientation which was a low index plane, low energy surface. Further, the second inclination was accommodated by the presence of kinks in these ledges, and these kinks obviously again put out low energy surfaces. Okay. Now, the total energy of the system can be calculated, the energy of the terraces plus the energy of the kinks plus the energy of the ledges, and interestingly, if you want to understand these ledges, again these are structural ledges, these kinks are structural kinks, and more interestingly, I can understand these kinks as a defect in a defect in a defect. So, this is a second order defect, because the surface was the first defect, the ledges were a defect in the surface, therefore, I call them a defect in the defect. The kinks are a defect in the ledges, therefore, they are a defect in a defect in a defect. And these kinks and ledges have very important role when you are talking about crystal growth. And for instance, suppose I have an crystal growing crystal, and suppose I had a flat surface like this, then the attachment of atoms to the surface would involve a nucleation problem. That means that an atom, this site would be no more preferred than some other site on the surface, and actually the atoms can diffuse around, and unless they attain a critical mass which is called nuclei, the crystal surface would not grow. But when you are talking about the presence of ledges, then these sites are high energy sites for atoms to come and sit here. So, you can see you can actually put an atom here much more easily as compared to the terrace. So, therefore, you have preferential sites now on the crystal surface for crystal to grow. Now, we had already seen that when you are talking about these kind of preferential sites, this ledge is very similar to the kind of step which is provided by screw dislocation terminating on the surface. We saw the constructive role of dislocations in crystal growth, and that surface, the role was similar to the role of a ledge in providing crystal growth. Now, kinks again would be a even higher preferred, even better preferred site for add atoms to come and attach. For instance, now if an atom comes and attaches here, so this will be the most preferred site, the next preferred site would be the side here, and the third lesser preferred would be the terrace. So, you have the kink sites have higher preference, the ledges of slightly lower preference, and terraces of the even lower preference when it comes to atoms attaching. So, the presence of these kinks and ledges which are defects on the surface actually help in crystal growth. So, though in this case we have considered them as to be arising out of the necessity of accommodating inclination on the surface. So, this is coming from the fact that I am inclining my surface with respect to the low index plane, and this inclination is accommodated not as a smooth cut, but as a breakup into ledges and kinks, because now that in that case the crystal will only be putting out those surfaces which have a low energy. So, this is the description of the surface in terms of ledges and kinks. Next we go to another important topic, which is the equilibrium shape of a crystal. Now, if the surface energy is isotropic, in other words, surface energy does not depend on the direction in which I am looking or equivalently the plane of the cut, then the equilibrium shape of the crystal is obviously going to be a sphere. So, if the crystal will be spherical if the surface energy has no preferential direction. In other words, suppose I make a cut in the crystal along 100 or 111 or even a 42, 3, 432 kind of an index plane, it would not make a difference, and therefore, the equilibrium shape of a crystal would be spherical. The equilibrium shape of the crystal should always be differentiated with respect to the growth shape of a crystal, because the growth shape of crystal would mean that the fast growing planes would exhaust themselves by growing fast, and the crystal will be left out with planes which are the slow growing planes, and that is very clearly different from the equilibrium shape of the crystal. Okay. Now, the equilibrium shape of the crystal means that now I am talking about the crystal is wanting to put out only those surfaces which are low in energy. So, this is clearly the difference between equilibrium shape and the growth shape of a crystal. Now, to obtain an equilibrium shape, of course, the crystal has to be annealed normally for long times, and the crystal has to slowly go into its shape, which is the least energy state for the system. But normally in usual crystals, the surface energy is not isotropic. That means it is going to be direction dependent, or is going to be dependent on the kind of plane I am putting out. The kind of cut I am making to make the surface is going to tell me what is the energy of the system. Okay. Therefore, there will be certain planes of a lower energy compared to certain other planes which have a higher energy. So, this point has to be kept in mind. Now, this energy variation of planes with respect to direction is captured is in a polar plot of surface energy, which is known as the gamma plot. And so, let me show that what is a gamma plot like. A gamma plot looks something like this. In other words, suppose I have, even though I have drawn the Cartesian coordinate, this is still a polar plot. So, what I am drawing here is that suppose if I am looking along this direction, this is my surface energy for this plane, but suppose I am working on some other arbitrary direction, for instance, my surface energy actually increases. So, this distance is proportional to my surface energy, the gamma. So, here the surface energy gamma has a certain value. So, this is, for instance, suppose this plane is correspond to the 0,1 plane, and this is some arbitrary plane, and therefore, the surface energy is increased. If you go further away, the surface energy increases even further, and then again it reduces when I go to a crystallography equivalent plane like 1 0. Therefore, typically in crystals the surface energy varies with respect to the angle of the cut. Now, if I already have a gamma plot, that means that I can determine the energy of any given plane or from the gamma plot. Of course, initially the gamma plot itself has to be determined, knowing the kind of surfaces the crystal has got. Now, the equilibrium shape of a crystal will be bounded by these low energy surfaces, and we will determine the crystal shape by something known as the Wolff construction, and which we will construct from the polar plot of the surface energy, the gamma plot. We will see that soon. So, having the gamma plot, we can use the Wolff construction to determine the equilibrium shape of the crystal, and the important thing about this equilibrium shape is that it will have the point group symmetry of the crystal. So, in other words, the whole mathematical concept of point groups and which have no what you might call physical basis or comparison with the real crystals, which have been derived purely mathematically, they converge with the concept of real crystals when you actually start talking about the external equilibrium shape, which will correspond to one of the point group symmetries of the crystal. Now, or to the point group symmetry of the crystal. Now, the important point to note about these gamma plots is that it typically has sharp cusps, and any orientation or any planes around this low energy plane will steeply vary with higher energy. That means the crystal, if the gamma plot has sharp cusps, then the crystal will tend to throw out those planes which correspond to these cusp directions. And in this initial treatment, we will just ignore the entropic effects, and we will just try to understand physically that how a crystal can have actually a low index plane as its surface. So, we already seen this gamma plot, we have seen that the energy of the surface varies with respect to direction, and it goes through a maxima somewhere in between at certain angles, but there are these sharp cusps in the gamma plot which correspond to certain low index planes. Now, what does this imply? That means that suppose I have a crystal having this kind of a surface, say for instance this surface, or and compare it with the surface which has this surface, a crystal. So, now I am making a crystal, and this is my low energy surfaces, but now I am making a crystal with a surface which has a cut something like this. Obviously, this surface will not like to be at this orientation and will want to rotate itself to a low energy orientation. In other words, this surface would like to want to go to an orientation like this, and this is the origin of the surface torque. In other words, the surface energy anisotropy or the variation of surface energy with direction wants to rotate the surface to a low energy surface, and this is something like a torque, and therefore, this is the origin of the surface torque, and this is why this anisotropy in surface energy makes crystalline surfaces different in very significant very different from the liquid surfaces where there will be no such effects of surface torque. So, this is something which inherently this concept of surface torque directly comes out of the study of these gamma plots, which shows the variation of the energy with direction. Now, how to get the equilibrium shape of the crystal from the gamma plot? As I said, we use something known as the Wolff construction, which we briefly go over here, but I am sure there are advanced texts where there can be more detailed discussions of the same. So, the way we do is that, of course, we have the gamma plot to start with. So, this is my gamma plot lines, and then I draw radius vectors from the origin to intersect the Wolff plot. For instance, I draw these lines like OA, which is shown here, OA, which intersects the gamma plot. I draw tangent line or lines perpendicular to OA like lines XY here, and now the figure formed by the inner envelope of all the perpendiculars is the equilibrium shape of the crystal. So, I draw one plane here at point OA, then I consider another point O B here, and then I draw my line joining the two, and then I draw a perpendicular here to this line, and then I calculate the inner envelope. So, this is my point B, for instance. I calculate the inner envelope of all these points, and that will give me my equilibrium shape of the crystal. Because this plot which I have shown here, the gamma plot, has sharp cusps at points like these points. Now, the inner envelope will actually consist of planes which are shown here, which is nothing but these flat planes here. And therefore, now my equilibrium shape of a crystal, this crystal in 2 dimensions is a square. and therefore, any kind of a gamma plot or any crystal having gamma plot with very sharp cusp tends to have a polyhedral outer shape. Of course, if entropic effects are taken into account, some of these facets may tend to get more smoothened as compared to this strict polyhedron, but in the ideal case when entropic effects are ignored, then you will see that this crystal is bound by faces which form a polyhedron, and the width of these faces is inversely proportional to the surface energy. That means, the largest faces are the ones with the lowest energy, which is obvious given the fact that the crystal will always like to put maximum area for those surfaces which have low energy. So, given the gamma plot, I can make the Wolf construction to determine the equilibrium shape of a crystal. So, let us revise some of the concepts we have come across during the consideration of surfaces, and some of these terminology may be new to us when we discuss surfaces. So, the important thing is we started off with that even though we call it a surface, it actually extends a few layers deep, and often the interior layers also have a profound influence on the properties of the surfaces. Now, for instance, and we can create, the second thing we saw was that the surface can be created by an angle of cut and the position of the cut, and when I create a cut, the two sides of this the two surfaces which I create using the cut may actually have different kind of surfaces, and this is very, very important. And when you do a cut, we can start with the simplest model, which is known as the broken bond model, where when we understand the surface as a termination of the bulk, and I need to go no further in calculation of the energy and other kind of aspects regarding the crystal surface. But typically, or in many cases, there could be a process which is known as reconstruction, and therefore, my surface would be altered in structure with respect to the bulk. When I write down the surface energy, I can see that I need to worry about the number of atoms per unit area on the surface, which is going to change obviously with respect to the inclination of the surface. I need to worry about the number of bonds broken on when I make this cut, and I need to worry about the bond energy per bond. Of course, initially we can start with simple metals like copper, where we can assume that the bond energy per bond does not depend on the angle of the cut. Then we try to differentiate liquid surfaces from solid surface, and the essential point we mentioned was that the liquid surfaces when I am stretching the surface remains unaltered in structure, but the solid surface can actually stretch. The solid surfaces require can be better described by surface stresses rather than surface tension, and additionally there is a quantity like surface torque which comes into picture when I am describing solid surfaces. Now, the surface of a any arbitrary inclined surfaces can be described in a crystal, can be described by terraces, ledges and kinks, and I can make actually a calculation of the energy based on the density of these ledges and terraces in a material. And the reason that the surface would like to put out these kinks and ledges instead of having a smooth surface at this inclination is because it would like to keep those low energy surfaces exposed rather than the high energy ones. We can we also saw that typically that surfaces are anisotropic in energy, and that implies that the equilibrium shape of a crystal is never going to be spherical, it is going to have a certain polyhedral shape, especially if in the surface energy versus orientation plot, which is known as the gamma plot, there are sharp cusps. Okay. And we use something known as the Wolf construction to take us from the gamma plot to the equilibrium shape of the crystal. So, let us do one example to calculate how we can use this broken bond model to calculate the surface energy of a crystal. So, let us try to calculate these some of the surface energies of a copper crystal. For instance, we will start with some simple low index planes like the 100 plane, the 110 plane and the 111 plane of a copper crystal, and try to calculate the surface energy of these three surfaces. Now, the data we require obviously is the bond energy per bond of this crystal, and this is B subscript Cu is 56.4 kilojoule per mole of bonds, and the atomic lattice parameter of copper is 3.61 angstroms. So, I will use the formula as before, which says that the surface energy, which is now joules per meter square, is the bond energy per bond multiplied by the number of atoms per unit area and number of bonds broken per atom. So, the difficult term in this calculation is the number of bonds broken per atom, because this requires a little visualization that how actually I am making a cut and how the number of atoms the number of bonds which are actually broken. The term half, as I pointed out, comes from the fact that each time I make a cut, I am actually creating two surfaces, and half the energy is expected to reside with one surface, other half is expected to reside with the other surface. So, let us try to calculate the surface 3 surface energies, the 100 surface, the 110 surface and the 111 surface, and as I pointed out, the difficult thing to visualize is the number of bonds broken per atom. So, now let us take the 100 surface and let us consider that suppose I have a central atom in this FCC copper, this is the atom sitting on the unit cell between these two on the face center, and I am making a cut which corresponds to this orange kind of a plane, which is the 100 plane. So, each copper atom is bonded to 12 atoms. So, I have 12, I can make this count 12, 1, 2, 3, 4, which is in plane of this in the plane of this plane 100. There are 4 behind the plane, which are these 4 which are behind the plane. This is 1, and then there is this 2, and there is 3, and there is 4 which are behind the plane, and there are these 4 which are in front of the plane. So, which I call the 1, the 2 and the 3 and the 4. So, 4 in plane, 4 behind the plane and 4 in front of the plane, making 12 bonds per copper atom. Now, when I make this cut, obviously all the bonds behind the plane are intact, the bonds in the plane are also intact, and I will assume all the bonds in front of the plane are broken. So, in other words, I am actually not cutting through the atoms, which is obvious, I cut a little in front of the atoms, so that I actually create a surface of the 100 type. Now, that means that now in this case I am actually having 4 bonds which are broken, 8 of them are intact, and this is the number I have put here. And for the 100 plane, the surface density is 2 atoms for a square area. So, that is my surface density, which you can see, because now this is my surface here, the 100 surface, and I can clearly see there are 4 contributing 1 and there is 1 in the center, 2 atoms, and the area of this square is a square. So, 2 atoms per a square, there are 4 atoms, 4 bonds which are broken, and the bond energy per bond data given is 56.4 kilojoule per mole, and therefore, I get a surface area of 2.87 or the surface energy of 2.87 joule per meter square. Now, let us consider the 110 surface. In this case, it is slightly more difficult to visualize, and of course, there are many ways of doing the same visualization, but let us use old tool which is using the cube octahedron. We have seen this solid cube octahedron which is obtained by truncating a cube or equivalently truncating an octahedron lying just between a cube and an octahedron. Now, in this, suppose I create a 110 kind of a cut, and so this my central atom which is sitting in right at the center of this between the 2 unit cells is bonded to 12 copper atoms around it, and these 12 can be counted as 1, 2, 3, 4 above, 1, 2, 3, 4 in the plane of the atom, and similarly 1, 2, 3, 4 below. All atoms obviously are same, but have been colored differently for better visualization. So, each atom is bound to 12 atoms, and this coordination polyhedron is my cube octahedron for the FCC copper. Now, when I am making a 110 kind of a cut, this is my orange plane, which is the 110 kind of a cut, which is shown here. When I make this cut, obviously again I do not cut through the atoms, I cut a little in front of the atoms. Number of atoms in the plane of the cut are 1 and 2. The number of atoms which are behind the plane of the cut are 5, and correspondingly there are 5 in front. Let me count the 5 in front, which are symmetrical to the 5 in back. 1, 2, 3, 4, 5. So, the 12 coordination number is coming from 5 in front of the cut, 5 behind the cut, and 2 in plane of the cut. So, that makes it 12. 5 in front of the plane are broken bonds, and therefore, this number 5 comes here, the bonds broken per atom. The area of the plane can be calculated, of course, by putting it in a normal FCC unit cell. Of course, this is my plane here, and this is my plane here in the unit cell, and you can see this height is 1 and this length is root 2. So, it is root 2 a square, and there are 2 atoms residing here, therefore, it is 2 by root 2 a square, and of course, I multiplied by the bond energy per bond to get 2.54 joule per meter square, which you can see is clearly different from 2.87 joule per meter square for the 110 plane. Now, let us consider, so we have used 2 different methods to visualize the cut, though all these could have been done in a single unit cell, but we wantedly are using multiple methods to visualize the cut and to calculate the number of bonds broken per atom.
This is maximum possible energy at the surface.
Oh, we will see just, so this is for the one, these are some of the low energy ones. Suppose you make an arbitrary cut, that will be even higher energy. So, this will be the,
actually if we see just before in that figure we can consider only four atoms, sir.
Which one? Yeah, here in this one.
Yes.
This one. Yeah.
Yeah, and if we suppose within the bulk, then energy will be low, I think.
Which one?
Just this one.
This one.
Yeah.
What will be low?
Energy at the surface, I think, should be more or low in compared to the bulk.
No, surface energy is always higher. So, the reference point for surface energy is the bulk. The reference point for surface energy is not the vacuum.
Yes.
So, this is a very important point you raised. Now, is the surface in a higher state of energy with respect to, say, suppose I consider the isolated atom sitting in vacuum free. Obviously, the surface energy is not that reference state. It is assuming that the crystalline bonded state is my reference state.
Yeah.
And therefore, the surface energy is calculated with respect to the perfectly bonded crystalline state. So, this is a very important point to be noted, and therefore, this should have, and whenever I am writing any interface energy, I am always assuming my reference state is not the isolated atom state, but my perfectly bonded crystalline state. So, this is a very important point. Surface is always in a state of higher energy, and therefore, atoms on the surface want to minimize their area, and that is resulting in my surface tension and all these surface stresses. In the case, of course, we have seen that crystalline surfaces can also have shear stress associated with them. Now, we will take an alternate view of finding out my 111 surface energy. So, to calculate the 111 surface energy, let us look at the way the 111 planes we constructed in the very first place. We consider the 111 planes by considering a central atom with 6 in a close packed layer around it. Then we constructed a layer by putting some atoms into these very positions, and then we considered the alternate set of voids formed by these and put the C layer. So, we had the ABC kind of packing to form the FCC crystal. Obviously, when I am talking about the 111 plane, each one of these planes we had seen was the 111 plane. Therefore, when I am making a cut, so this plane is my plane of the cut, plane of the cut. Therefore, when I make up, of course, again not cutting through the atoms, a little above I will shift my cut. I can see that all the bonds in the plane, which are 6, are intact, 3 below are intact, so only 3 bonds are broken. So, these 3 atoms are no longer bonded when I make a surface. So, the number of bonds broken is 3. So, my perspective, the way I am calculating the bonds broken per atom has changed, but this makes me easier for me to calculate the bonds broken per atom. My surface area I can calculate again by simple geometry to be 2 atoms per root 3 a square area, and my energy for the surface comes out to be 2.49 joules per meter square. So, let us compare it with the two values. It is 2.54 is more, and this 2.87 is even higher. So, this is my least energy surface in copper, and this is not surprising because we know this is my surface which shows the close packed planes. So, these are the closest packed highest density planes which are the close packed planes, and therefore, I expect this to be the lowest energy. So, using the example, we have tried to calculate, of course, the very simplistic way the surface energy of various kinds of planes in copper. Of course, I could consider even lower index planes and try to calculate their energies, but at least for comparison we have 3 rather low index planes, and therefore, we can find which is the lower energy of these 3.